Okay, we are now continuing our courses in fundamentals and biomedical application of quantum mechanics science. And you know, I'm expanding many lectures, give you the fundamentals. And the last lecture, we saw one of the most important principles in this quantum business, which is the Heisenberg Principle. And Heisenberg said something very interesting to us. He said that when we considering the localization of a particle that's represented by a wave, it cannot be a plane wave. It has to be a wave package. It has to be a kind of space filled with waves, right, that propagates with the velocity of the particle. And the way to do that was to add up momentums of a particle, which had an interval, delta p. And that causes a localization of the particle, delta x. Delta p is how many momentums we have to add up. And momentum for us, remember, from de Broglie principle, right, hypothesis, this means different wavelengths. So we are adding waves of different frequencies, different wavelengths, and then we can localize the particle within a delta x. And that was established by Heisenberg in a more elegant way, in a more appropriate way, which is that way. You know, if you do formally, you know, and then it's a little bit more elaborate, using Fourier transform and everything, variances, we can get that for a particle that it has some momentum and some imprecision of the momentum, the localization of the particle is basically such that the product of the momentum variation and the position variation is h divided by 2 pi. H divided by 2 pi is normally what we call h bar. And that's a formal way. When we work with variances and everything, we're not going to do that because, you know, I'm trying to explain to you as much as I can without to be too formal. But this is very interesting, this principle, because this imposes many limitations. Because basically we transfer or we translate this principle saying that if I measure very well where the particle is, I cannot know the momentum very well. If I measure very well the momentum, I cannot know where the particle is. Basically, when delta p goes to 0, delta x has to go to infinite. But when delta p goes to 0, we collapse to a single wave. We know a precise momentum, de Broglie wave. But then the wave now is a plane wave that occupies the whole space, and delta x goes to infinite. So this is important. And it's important in many contexts. Right? As I'm going to show to you now. Now, because the position and momentum is quantities that are related with energy, having variations on the momentum. Oh, by the way, before I go on with this, let me tell you that this is a limitation on the resolution of microscopes. So this is what we call Heisenberg limitation. So when you look into something in the microscope, if you know exactly the position, you don't know exactly the energy, you don't know exactly the momentum. You cannot know. Therefore, to have a spatial resolution means momentum resolution. And that gives you some limitation. Because when we put light to see, we always change the momentum a little bit, so we change the resolution in the space, and this turns out to be a limitation. Okay, now I'm going to do something, because as I was telling you, because momentum and position are so important for the energy, right? Those are the variables that determines the energy. I'm going to do the following. Delta p times delta x is h bar, right? Bigger equal than. I'm going to multiply and divide by P, multiply and divide by M. It turns out that this first term is basically the variation of the energy. If you take the variation of energy, this 2 gets here, then I get 2 times P delta P, the 2 cancel. So this is actually the variation of the energy of the particle, which I'm going to call delta E. And m delta x divided by P, if I substitute P by mv, delta x divided by V is the time that the particle is living in that region. So delta is delta T. So the same principle that we observe, Heisenberg Principle for the momentum, now turns into also a principle for energy. The energy that I measure of a particle or I determine is related to the imprecision of when I measure that. And the product of those imprecision is h bar. It's limited by h bar. So all those limitations, they are important because we're going to see that atoms have levels. But if I determine the level, if that's, the particle has to stay there by an infinite time. If there is an imprecision on that, means the particle may not be there anymore. So I create a lifetime for the levels or the excitations of the atom. Or these two ways of expressing the same principle, which is delta P times delta X is basically limited by h bar, and delta E, energy, times delta T is also limited by h bar, is very, very important. And to show the importance of this, right, to show the importance of this, let me give you an example, the consequences of those principles when we have a confined system. Because this is important not when I don't care where the particle is. This is important when the particle is for sure is in some region. Then I have a problem. Okay, so let's consider a very, very simple example. You have a particle that you know is confined in a box. You know, it can be an electron in a piece of metal. You know that the electron has to be inside that part, that size of metal or anything. And so I know that the particle must be within this space. That here I'm considering 1D, one dimension. So I know that the particle must be within a delta x that's on the order of L. The particle cannot be outside this, because that's the size of the box. It turns out that because of the uncertain principle, this particle can never have zero energy. Let me show you why. The energy of the particle is half of mv squared, right? And then the way to do this is multiply by an extra m divided by m, and this is p squared divided by 2m. That's a nice way that we like to represent the energy of a particle free in some position of the space in terms of other potentials or other energies. It's not free to go anywhere, but within the box, this is the energy of the particle. And we know the localization is L, because we are sure the particle is somewhere in this box. Now, the minimum I can have is the momentum equal to the imprecision. That's the minimum I can have, right? That's the best I can do. If I go to the minimum momentum, we ask, I want to go to the minimum energy, the minimum momentum of the particle. How is delta P? Well, delta P has to be on the order of P. In this case, if I apply the uncertain principle, I get that this is L here, delta P. I get that the momentum of the particle is basically h bar divided by L. So if now I have a momentum because the localization of the particle, I have an energy. So quantum mechanically speaking, when I localize a particle, means that I cannot have zero energy. Or I cannot have energy equal to zero. The energy has a minimum that normally we call ground state. So the ground state of a particle that's confined is a consequence of the uncertainty principle. Because if the particle is confined, it cannot be confined to delta x equal to zero. It has some dimension. And the particle will be there forever. But that as a consequence, because they are waves, we can get this in another way, in another point of view, by waves in a different way. Am I going to do that soon? But just using the uncertainty principle, that we learned that for this particle be represented by wave means that the wave has to occupy this space. And for the wave to occupy this space, it cannot have momentum equal to zero. Because momentum equal to zero will be too big wavelength. Basically, this is what's behind. And then I calculate P, and P squared divided by 2m is the energy. So a particle that's confined must have a minimum energy. The concept of ground state, the minimum energy, is important everywhere. Nothing really has zero energy, or what we call zero energy is some finite value. That's dependent on h bar and depends on the confinement. For a particle in a box, it cannot never have energy below h bar squared divided by 2ml. If I make L very big, very big, very big, this energy comes down, down, and down. And then eventually, on the macroscopic dimension, we think that a particle is stopped in there, right? Because this is comes to the contest. Now, you can imagine another situation that's very important. A harmonic oscillator. You know, harmonic oscillator, you have an energy that's dependent on x squared. I call omega square. So this is like saying that the potential is half m omega square x squared. So this is the total energy. We learned from high school that the total energy is the kinetic energy plus the potential energy. And I put the, in the boxes, the energy is infinite everywhere outside the box, so the particle can never be there. Now I put a boundary conditions that's soft. It's varying. The particle can be localized here, but depending on the energy, can be different places. Right? Harmonic oscillators is one of the most precious potentials that we have in physics because almost everything oscillates. Almost everything has a kind of association with the harmonic oscillator. Okay, now my question is, what is the minimum energy of this? This has to be the energy. But there is a compromise between momentum and x. Because at the minimum, this has to be as small as possible. But as small as possible is like going to the minimum, going to the uncertainty principle, where P and X is bounded by h bar. And I put the 2 here because normally that's the way that will come. But that's not, you can find in the internet the calculation of this, because what we do normally is we rewrite the energy and we minimize the energy. By minimizing the energy, because now we have a connection between P and X, we get that the minimum energy for a harmonic oscillator is half h bar times the oscillator frequency. So that means that when we look in here, the particle cannot really stop at the bottom. Always going to have a minimum energy, which has this value. This is another example. I didn't go in detail anything from this, but in the harmonic oscillator, the best way is put like this, but work with the variance to get the minimum. And this is right. If you do right, this is right. And I can ask that in some problem for homework that we're gonna discuss. So you see, the fact that particles are localized and they are wave, and I have to localize them, means that I create imprecision. Creating imprecision, what I have is, I have some consequences. There is a compromise between position and momentum, or energy and time, and they are bounded by h bar. H bar is very small, but in the microscopic world, this became huge, right? This became huge. And we learned that by adding those waves, we create the imprecision, and one of the most important consequences is that localized system cannot have zero energy. They always have a minimum energy that we call the background energy, or the fundamental state, right? The fundamental energy is the one that we obtain for a confined system, and being compatible with this relation between position and momentum, following the energy. That's what we have. Okay, so we learned that to create packages and everything. Now let's move on. We're going to continue moving on, and we're going to move to atoms, because you see that the quantum mechanics, it is a physics of the tiny world. That's where I cannot avoid quantum mechanics. When I come to the macroscopic world, sometimes I can avoid, because h is small, and that as a consequence, everything we are saying on waves is also small. When we come inside the atom is tiny. You know, I told you before that on the atom, the de Broglie wavelength is on the size of the atom. So I cannot avoid the wave mechanics for the electron in the atom. I cannot. Okay, so we're going to move to the atom, because this is interesting. And we're going to give you one more step before we formulate the master equation. You know, Rutherford gave to us a nice contribution, showing that the atom is made of this nuclei, which is a core with the positive charge, and the electron is going around, movable. Whatever we put or take charges for anything, we put and take electrons. And then by doing experiment with scattering, Rutherford, right? He creates the idea of the planetary atom, electrons orbiting around the nuclei. The nuclei is 10,000 times smaller than the atom itself. But you know, electron going around like this is unstable. Why is unstable? Because a charge that oscillates generates an oscillatory field. And an oscillatory field, electric field, and magnetic field is a radiation. And radiation has energy on it. So if I just have this atom as a classical motion, it does not sustain. I can mechanically find what is the frequency and everything that this goes around. But by the electromagnetism, this guy dissipates. It sends electromagnetic waves out. And then the electron actually will never be in this orbit, but will spiral out, spiral in, and collapse. And this, so that comes the instability. So this unstable system cannot sustain. So we know that atoms exist, so classically this cannot be true. Now, if this is a wave in here, the wave will survive in a way that maybe we will avoid those classical limitations. Well, on the top of that, people has done experiments observing what radiation comes from atoms. So I have a gas, I give a discharge in the gas, you know, light comes out. I collect a little bit of this light. I split this light out. I divide, right? Separate in different colors. I put a prism here, but you can do it with diffraction grades and everything. So I split. And when I split, I record. I see that actually the discharge in the gas, which is the energy coming from atoms, is made of discrete lines, which are the spectral lines. So not only the atom violates the classical concept of the electromagnetism because the electron cannot stay around because it dissipates in the form of radiation, but also it seems to be strange that not all energies are possible. You have a discrete sequences of energy that are coming out from the atoms. Well, this concept was investigated by Bohr, and Bohr proposed a nice concept. Bohr proposed that, look, we have to think in a different way. The electron in the atoms are stable. You know, the model of Niels Bohr is the model that really will force us. And why I'm doing this? Because I'm going to show to you that Bohr proposed a few concepts that he observes, but actually the quantum mechanics, the concept of associated with the electron inside the atom, a wave, explain everything, right? But you have to know what are the observations and what are Niels Bohr model for the atom. So he said that against what we believe in the classical mechanics, the orbits are stable and they don't emit radiation. For magic, they don't do it. And he somehow knows that something has to depend on the h bar inside. And he said, look, the angular momentum is not any angular momentum that I can have. I have a few angular momentum, and they are an integer number of h bar. H bar, actually, the Planck constant, has units of angular momentum. And finally, he said, well, they may have many energies inside, depends on the orbits. And when the electron moves from one initial orbit to a final orbit, there is a jumping of orbits. There will be radiation emitted with some frequency, and that's dependent. Because there are discrete orbits, there are discrete radiation being emitted that explain the lines, the spectral lines. Okay, well, everybody's happy with that. It's explaining what we observe. You know that when I have an electron, when I have an atom like this, if I have an atom like this, I have for the electron, I have the kinetic energy plus the potential energy that's given by the electrical attraction. So normally the energy of the atoms is written by this, and the orbital angular momentum is given by what Bohr proposed. Now, if this is true, we have a relation between velocity or momentum and position. Right? So by this, we have the velocity. And we know that the orbit will be stable when the radiation force, the electrostatic force, the nuclei pushing the electron, equal to the centrifugal force. Right? This is classical, doing the classical mechanics of the orbit. And that gives us a radius. If I put in the place of V, this number, I get radius that, so it's not any radius that I can have. I have specific radius. But I have also a relation between the radius and the momentum. So I put everything together in the energy. I end with energy, values for energy that are discrete. Right? So putting everything together, following the Bohr concepts. I have this. So actually we have discrete orbits. We don't know why, but we do. And we have discrete energies following this simple calculation. And of course, following Bohr, always that you have a jump of the electron from one place to the other. You see a radiation coming out, of course, because it's the electron jumping. It generates oscillatory electromagnetic field in that frequency. And then we see the spectral lines. Everything seems okay here, right? But, and then the Bohr's model, new Bohr model for the atom was a big success. They could explain everything they were observing, basically. There are some details between the lines and everything, but they could explain quite well. But the big question here is why? Why the proposition of Bohr works so well? Why the atoms obey? The electron inside the atom obeys these principles. And the answer is obvious to you now. It's because of the wave nature of the electron. If we associate with the electron a wavelength that's dependent on the momentum in some orbits, we can have orbits that are very specific. So imagine I have here the nuclei, the electron is going around, and I'm going to put a wave in here. This wave can overlap in one turn the way we want. Right. Any way we want, we can make the wave. But then there are big interferences. If we don't match some conditions, because now, following Bohr, there is a stable orbit. So this is the space available for the electron. But if the electron is a wave, that must be occupied in a precise way, because if I go 2 pi around, I have to come to the same point. It's not any wave that can be here in this orbit. The length of the perimeter of the orbit, or the size of the orbit, the length of the orbit, has to be an integer number of the de Broglie wavelength. Because that's a way to match well the wave inside the space available. It's like the particle in a box. I have zero wave at the wall here and here. I can only match some waves in here. It's like a string, right? We did that when we reviewed the waves. It's not any wave in a string. That's why a violin has precise notes, because it's only specific waves can be accommodated in that space. If you move your finger, you change the space. Okay. So let's consider that the electron is a de Broglie wave. Therefore, the wavelength is h divided by mv. And that in one orbit, the size of the orbit, which is 2 pi times the radius of the orbit, must be an integer number of lambda. Right? But in the place of lambda, we put h divided by mv. It turns out that gives us exactly, when I multiply this here, mv times r is the angular momentum. And the angular momentum, in this case, is an integer of h bar. Exactly like Bohr predicted. So, what Bohr observed for the existence of the electron orbits in the atom is actually a consequence of the electron being a wave going around the atom somehow. It's a stationary wave, or a stand wave on the orbit. And this stationary wave cannot have any configuration. You must have an integer number of de Broglie wavelengths to perform the orbit. Well, that seems to match very well with the Bohr principle, right? And it's not a coincidence. It's just the fact, because inside the atom, the electron is where it can actually be a wave. We still needed to answer wave of what? This is something we needed to answer. And I'm preparing you for the wave behavior then to say wave of what is that, right? So I'm just somehow preparing you with all, make you accept the wave behavior for everything we're doing, and then we're going to discuss wave of what. Okay, so you see that the electron is always a wave, and this is the most important thing for what we're going to do. But not only the electron, right? Everything else that has momentum, in some situations, will behave like wave. And we are almost at the edge of the concept that people create 100 years ago to establish really the formalism of the quantum mechanics to understand everything else. Because we know those very simple situations, but now we're going to deal with big molecules. We're going to deal with many other things that we must know how to deal with. And to do that, we have to evolve the concepts. We have to step up the way to describe it, because we may have situations that is not only the angular momentum. We have many other things that are necessary to describe physically the system, and therefore we have to know how to deal with that. But most important, we have to know waves of what. And I'm putting this question all the time, so you get curious enough, so I can give you the interpretation in the right moment. Okay, very good. So we are now basically in the point where some other scientists will start to construct the formalism that we need to understand any physical system we want. Okay, well, in the next lecture, I'm going to start to formalize. We're going to start to generalize. Okay, well, but you think that this is valid only for box, for oscillator? We want to be more general. You are able to draw this wave here in the atom, even though you don't. Oh, by the way, you see, I made a wave with many bumps, and I can make waves even with more bumps, right? I can make waves with even more bumps, and as much bumps as I have means different states. More oscillation, higher energy, and that give you all the energies that we found there, where we get the famous relation for the energy, that is the energy of the atom of one electron is minus half mz e to the fourth divided by h bar n square, where n is equal to 1, 2, 3. If n is equal to 1, I have the most is 1 oscillation around the orbit. If I have 2 is 2, 3 and 3, and so on, right? So the waves will be more and more. When I go to any infinite, I almost don't see oscillations anymore. This is a very high excited, it's almost like a free electron, and then it's going to become free anyway. Okay, so enough for the present lecture, and then in the next one, we're going to start, as I said, we're going to start to formalize a little more, to apply this concept in a more generic way. And then finally, we're going to construct the equation. But I promise to you, before I construct the equation, I have to tell what is the best interpretation physics can come. Wave of what? Right? We know that the wave behavior is explaining almost everything, but we have to know wave of what. Okay, see you in the next lecture.